Thanks very much. Thank you for being here. And it's really nice to be able to speak on this wonderful day of celebration of Peter Shor's Breakthrough Prize in Physics. Congratulations, Peter. And yes, you're right. This is a talk about algorithmic fairness. So, since physics came up earlier today, there's this wonderful video on YouTube of Richard Feynman talking about how do you develop a new law of physics. So first he says, you guess the law. That's where the physics comes in. And then you compute the consequences of your law. What should you expect to see if your law is in fact a law of physics? Then you design experiments to try to tell whether you're going to see these things that you have computed. And then you test, you compare your experimental results to your predicted results. And you want to know, did your law pass the tests? And what he says is, if what you observe doesn't match your predictions, then your law is wrong. It doesn't matter how beautiful your law is. It doesn't matter how clever your law is. It's just wrong. On the other hand, if what you have predicted does coincide with your experimental results, all you know is that your law has not yet been invalidated. And so you should compute more consequences and so on. So ultimately, what you want is that no experiment should distinguish your law's predicted consequences from reality. Okay, so why am I talking about this? Let's switch to a setting for algorithmic fairness. Prediction algorithms assign scores, let's say between 0 and 1, to individuals. And these are often interpreted as probabilities. So what is the probability that person X will commit a violent crime in the next 2 years? There are prediction systems that try to answer this question. The problem is, what is the probability of a non-repeatable event? You should not assume that X is represented to the algorithm in a way that many, many other people are also represented. And we're just taking the probability over those people who all collided at that representation. Rather, the representations are rich. We don't expect collisions. And so we can't sort of say the expectation over people that looked like this. This is a unique person. So this is not a question we're going to be able to answer. It's a question that is a topic of interest in the philosophy of probability and has been for decades. We don't even know whether non-integer probabilities exist. Maybe everything is completely determined, but we don't know what the future will bring because we don't have enough computational ability or enough information. But maybe there's no uncertainty. Maybe there is uncertainty. Maybe there really is somehow or other a concept of this is 50-50. This is 70-30. We just don't know. Now, making predictions like this is what AI is all about. So since we don't know what the probability of a non-repeatable event is, this really is the defining problem of AI. Like, what is the definition? What is this thing we're trying to do? Or just stepping back a little bit, what are the properties that the scores of an ideal predictor will satisfy? Suppose I give a score of 2/3. How do we ever test that 2/3 was the right answer? I mean, eventually, either this will be a positive or a negative result. But how do we test? We can't. So we don't even know what we want from the ideal predictor what on earth should we ask for from our own predictors that are not ideal? They won't be perfect. Okay. So tying this back now to Feynman's talk about a law of physics, we want to build a predictor. In this talk, whenever you see a tilde, that's something that we built. That's not nature's probabilities, that's our prediction algorithm. So we can think of the predictor that we build as a scientific theory that maps individuals to a number between 0 and 1. So one thing that we could do is we could specify a collection of distinguishers that whose functionality I will explain in a moment. That's drawn at the bottom of the slide. Okay. But from computer science and complexity theory and cryptography, you probably have some kind of an intuitive notion of a distinguisher. So what we want to do when we actually get around to defining our distinguishers is that we want to require indistinguishability of the world according to our physical law predictor P tilde and its computed consequences from the real world, which are our experimental observations. So we want somehow to pass a collection of tests. So in the sequel, for the rest of the talk, my individuals are going to be denoted by I. And this is an individual as represented in the data, because obviously we only feed representations of people to the algorithms. But we're going to permit the possibility that there will be no collisions in the representation mappings, that every two people could be represented by completely different feature vectors, I. Again, P tilde is going to be the value of the predictor that we build on individual I. And we're going to let O tilde denote a draw from a Bernoulli distribution that has probability P tilde of heads. So if the predictor is, let me turn on the cursor, the pointer. If the predictor predicts a probability, say 2/3 for individual I, then O tilde sub I will be a draw from a Bernoulli that has probability 2/3 of coming up heads. So these would be the computed consequences of our model. And OI star, whenever you see a star, that's reality. So OI star is what actually happens. What is the true outcome in real life to individual I? So now, thinking in terms of distinguishers, imagine that we sort of have two experimental setups here, right? On the left, we are feeding to an algorithm a representation of a person, the prediction that the algorithm gives, and what actually happened, OI star. And our algorithm will produce an output, 0 or 1. That's the functionality of distinguishers, as usual in computer science. In the experimental setup on the right, we feed, again, the individual I, again, the algorithm's prediction, but this time, the computed consequence, the draw from the Bernoulli distribution with the parameter given by the algorithm's prediction. And so the notion of indistinguishability that we'll be thinking about is that tests should not distinguish these two. Okay? Now, let me step back a moment into the theory of algorithmic fairness to give you the backdrop for where this comes up. So the theory, we started laying out the theory in about 2012 and trying to think of what could we want from a predictor or a machine learning system. We thought of two flavors of fairness guarantees or fairness definitions that we might wish to enforce. The group version and the individual one. Group definitions are basically statistical properties of some sort. So for example, Maybe you have a population, maybe you're admitting people to a university. Statistical parity would be a condition that says, or it's also known as demographic parity, that the demographics of the accepted students should be like the demographics of the population as a whole. That is an example of a group fairness condition. Another example, so if you live in a country that happens to be 48.7% female, then 48.7% of the population in the school should be female. So group notions are very intuitive, but they fail under scrutiny. And here are some of the things that go wrong. Oh dear, sorry. I wanted to give one more example, because we're going to need this a lot. This is calibration. So first of all, let's talk about what it means for a function to be calibrated. A scoring function, remember, is assigning a score between 0 and 1 to each individual. Think about forecasting, weather forecasting, where the weather forecaster is assigning to each day in sequence the probability of rain tomorrow. So let's say that the forecaster is, discretized, and it's producing numbers like 0%, 10%, 20%, 30%, and so on. So calibration for the forecaster says, if we look at all of the days on which the forecaster said 30% chance of rain, then on about 30% of those days, it should have rained. And similarly for 70% and so on. Now, calibration has been central in the forecasting literature since at least as far back as 1982 in seminal work by Philip David. In the fairness literature, Kleinberg, Mullainathan, and Raghavan proposed it as a fairness condition. They said, suppose you have two demographic groups, let's say S and T, then we don't just want that the scoring function should be calibrated on the population as a whole. But in addition, we want that if we look at the members of S only, the scoring function is calibrated on them. And simultaneously, if we look at its behavior just on the members of T, then it's calibrated on that set as well. So it's a stronger condition. The idea that you might want your predictor to be calibrated on multiple sets, that has a history already in the statistics literature, the forecasting literature, for example, by, I think, Foster-Vora and Sandroni. But as a fairness condition, Kleinberg, Mullainathan, and Raghavan said, if the scores are calibrated, then somebody who looks at a score and is, let's say, evaluating a candidate based on the score has no need to second guess and to say, this score means something different in this population versus that population, because it's calibrated in both groups. So the meaning of the score V is the same. A V fraction of these will have positive outcomes. Just because something is calibrated, though, doesn't mean that it's fair. If it's not calibrated on both groups, you want to fix that. But if it is calibrated on both groups, it's not necessarily fair. So for example, imagine that we score people, and then we apply a threshold to the scores in order to decide admission for something or hiring or something like that. And suppose your calibrated forecaster gives the average score to everybody in set S, average among S, like what is just the overall base rate of probability of success for the guys in S. But for the people in T, it gives very, very refined information. And it scores some people at 0.95 and 0.9 and 0.85 and so on and so forth. Then if you have a high threshold, nobody in S gets hired, and some people in T would get hired. So while lack of calibration on different groups is a bad thing, calibration on different groups is not a guarantee of anything. Okay, now, my claim is that group notions fail under scrutiny. So here are some of the things that go wrong. Let's suppose you're an advertiser, and for some reason you don't like group S, but you do like group T. And you have a steakhouse, and you are required to proportionately advertise equally in S and in T. So what you could do is you could find the vegetarians in S and advertise to them. They're not interested in your steakhouse. They're not going to come to your steakhouse. So in some specious way, you are satisfying demographic parity, but you are not actually being fair. There's no way that this is fair. Or you might have some other method that somehow rewards or it observes demographic parity, but it rewards, accepts, promotes maybe people in the minority group that dress and arrange their hair and so on more like the majority. Okay. So this is another way in which you can satisfy the condition, but in a gut sense, you're not doing the right thing. It also can be surprisingly hard to test very, very simple notions of group fairness. This is an article about criminology and police behaviors and stops. And they show problems with benchmarking that have to do with subtleties in the choice of the denominator. For me, the nail in the coffin of this are a pair of results, one for classification functions, one for scoring functions, showing triples of very, very natural desiderata that cannot exist simultaneously unless the base rates for the two groups are the same. So so this. Okay. There's another question, which is if you are going to be making requirements for different subgroups of people, how do you choose these subgroups? We'll talk about that a lot later. Okay. So group notions are found wanting under scrutiny. Individual fairness is a different concept, and it says that you want to treat likes alike. So people who are similar with respect to a given classification or scoring task should be treated similarly. And this notion has great intuitive resonance, and it has also a strong legal foundation. The idea that similar people should be treated similarly, similarly situated people should be treated similarly, is foundational in law. Yes, Ronit?
So I'm just trying to understand, according to that definition,
yes.
the classification decides if I'm in the group. How is that different?
So this says for every pair of individuals, if they are similar with respect to this particular task, they must be treated similarly. It has nothing to do with which groups they're in.
What if the classification task tells me if they're in the group? So if I'm in the group and you're in the group, we're similar according to that classification.
Right, so that might be a case in which there's a clear answer. But if we're in different demographic groups and the question is whether we should be admitted to law school, what makes us similar won't be our group membership, it will be our intellectual interests and pursuits. And that's why it's I haven't gotten to the next line, which is, the difficulty with this approach is that for every task that you're interested in, you need some kind of a metric, a way of expressing for each pair of people how similar or dissimilar they are for this particular task. So going, like my favorite example is Ronit and I have very similar interests when it comes to, say, recommending papers in computer science to us. But for hair products, we would be perhaps completely different. So because we have different hair types. So the advertising hair product task is very different than the recommender system for technical articles task.
This is actually a terrible example because they've asked you for your recommendation of hair products.
Only Ronit. Okay. So this is a problem. The fact that you need a metric is a problem. If you have a metric, it turns out there are all kinds of great things you can do. You can come up with fair classifiers. You can train a classifier on a subset and generalize to the rest of the distribution while maintaining both accuracy and fairness. There's a lot of stuff that you can do. But where do you come up with the metric? So that kind of brought that avenue of exploration to a halt for a number of years. But there was this really wonderful breakthrough by Cristina Ilvento, who talks about how you can interact with a wise human, trusted and trustworthy human arbiter in a reasonable way, somebody who actually can tell you distances but can't articulate that into a mathematical, closed form or something. So how can you interact with such a person without exhausting them and asking all n-squared pairs in order to learn a good approximation to the metric? And this has been a very interesting direction. Okay. So the metric is problematic. My belief is that if you have any system that people really believe is fair, then by interacting with that system, you can actually extract the metric. And some version of this conjecture was proved a couple of years ago. Okay. So we have group fairness notions, which have their problems. We have individual fairness, which requires the metric. So the world isn't ideal. And in an effort to maybe make progress and go in between these two extremes, we have what I call the multi-X framework. So a pair of research teams, independently but simultaneously, started looking at a situation like this. This is supposed to indicate that we have a large number of large and arbitrarily intersecting demographic subgroups. And the word multi is to remind us that we have a large collection of groups. The word X is a placeholder for some kind of a fairness condition. So the general idea is that there will be a collection C of subgroups of the population. Whatever our requirement is, it will either have to apply simultaneously to every set or maybe every pair of sets or whatever it is. But it's a statistical requirement that is working on sets. And then the X will tell us which group fairness guarantee are interested. So you might have, for example, multi-parity that would make the demographic parity requirement sort of hold for different groups simultaneously. Or you might want equal false positive rates across all the different groups. Now, before we get into the particular X that I'm going to spend most of the time on, we have to say just a little bit about the set collection. So first of all, the sets, which sets should you be making requirements about? It sounds like a new problem, but this is really an old problem. So there's a big statistical literature on creating synthetic data that captures some properties of the real data. Which properties? It's the same question. You're building a model of something or other in order to predict something or other else. What are the features that you wish to be able to predict? It's the same kind of question. So it is an old issue, but it's arising in this new context. And there is the question of who chooses, who's responsible for choosing. Right now, don't worry about that. We will talk about it later a lot. But for now, just think it's just a pre-specified collection of demographic groups. Okay. So now let's talk about two kinds of conditions. For some alpha greater than 0, for all alpha greater than 0, given a set S, which is a subset of our universe, we say that our predictor is alpha accurate in expectation with respect to this set S if the following happens. If I choose, the expected value of the difference between the prediction probability and the actual outcome in absolute value should be bounded by alpha. So this difference is just the difference between the expected value of the prediction and the expected value of the outcomes. So this should be less than or equal to alpha. Okay? And then we say that if we have a collection of sets now, the predictor is C alpha accurate in C alpha multi-accurate if it satisfies this condition simultaneously for all of the sets in our collection of sets. So within this set, the predictions are right on average. Multi-calibration is a bit stronger. Similar flavor, but a bit stronger. It says that for every prediction value V in the range of our predictor, if I focus only on, within the set S, if I focus only on the people in S for whom the predictor has predicted V, then that should be approximately right in expectation. So this is the prediction, it's V, and here's the expectation for those in S for whom we've predicted V of their outcomes. That difference should be bounded by alpha. And again, if you have a collection of sets, the predictor is C alpha multi-calibrated if it's simultaneously alpha calibrated for each individual set simultaneously. Okay, so just in pictures, here is my universe of people, and in yellow I have the people for whom the predictor is saying 0.1, in red the 0.2s, in purple the 0.3s, and so on. And then we look at any set T in our collection, and we look at the slice of T on which the predictor, say, is saying 0.3, then a 0.3 approximately fraction of those people should have positive outcome. So that's multi-calibration. We want this to hold for all the sets T in the collection. So notice that a multi-calibrated predictor is describing the world as it is. It is not trying to do any kind of affirmative action. It's just saying this is the probability of success. Whether this should be the probability of success or whether it's fair that this is the probability of success, that's a totally different story. So if you're really thinking about fairness, the way you have to think about the whole line of work surrounding the multi-X framework is we're trying to understand the world as it is. It's a lousy world, perhaps, but we're trying to understand the world as it is. Then maybe when we've understood it, we can figure out how we wish to make adjustments. But the adjusting phase hasn't happened in the literature. I mean, there's been some stuff on fair affirmative action, but there's very little. Okay, so what is the framework for multi-calibration? It's a learning framework. We want to learn how to estimate what I'm calling PJ star. It's a star again. Star means it's reality. Everything we do is agnostic as to whether real probabilities are integer valued or they can live between 0 and 1. I like to think about them as maybe living between 0 and 1, but it's not required for anything that we're doing. And again, we can think of it as an individual probability for individual j, but we really don't know what that means. It's just a mental hook that I find helpful. Now, we're trying to learn to estimate PJ star given only integer outputs, 0, 1 outputs. We can never see in training data what real probabilities are. We don't even know if they exist. So we're trying to learn this only from Boolean labeled data. Of course, our algorithm then never sees any underlying probabilities. We don't know they exist. We can ever know whether we're doing the right thing unless we're only producing integers, and then we can see when we make mistakes. But we're not going to, that's not going to be the typical case. Even though we can't do that, we can test some statistical properties of the predictors, including multi-accuracy and multi-calibration. So again, remember that OI tilde is a Bernoulli draw from PI tilde, the predicted probability. And we can test things like whether the average predicted probability minus the average success is accurate. And that's actually the same as testing whether the draws from the predicted probabilities in expectation look like the outcomes in expectation. Because OI tilde is Bernoulli from PI tilde. So this blue term is equal to that blue term. So requiring the difference between this and this to be small in absolute value is saying that the predicted world looks like the real world on average on sets in our collection. That's now a collection of statistical tests that we can carry out. Okay, so there's a lovely algorithm. You might be able to think of others, but here's a lovely algorithm due to Aber Johnson et al. That I'm going to describe for you now for building a multi-calibrated predictor, assuming that we have our hands on sufficient training data. Okay? And it's not an insane amount of training data. So I'm going to describe something, and what I'm going to describe actually will correspond to building a circuit. So I'm going to describe it now, and then in a slide or two, we will look at the circuit. So the first thing is, we start out with a trivial prediction. So this isn't really happening. We're really building a circuit to do this. But the import will be to assign to each individual an initial trivial prediction of, let's say, a half. It doesn't have to be a half. Anything will do. Doesn't matter at all. As a matter of fact, this whole algorithm can be applied as post-processing to an artisanally created predictor that you have been building over your last 20 years or 20 months or whatever it is. And what we're doing won't actually hurt what you've done and will also ensure multi-accuracy. Anyway, so we initialize it arbitrarily. Now we have a collection C of sets. So what we're going to do is we're going to look for unhappy sets. What's an unhappy set? Well, our goal is to be multi-accurate. So an unhappy set is one where the accuracy in expectation condition is violated. If there are no unhappy sets, we're done. All the sets are happy, all the multi-accuracy conditions are all satisfied. If we find an unhappy set, then we're going to nudge the values for the members of that set. We're going to update our predictor, PI tilde, by nudging them in the right direction. If on average we were too low before, we'll nudge them up a little bit. If on average we were too high before, we'll nudge them down a little bit. And we might need to project onto the 0-1 interval if we've pushed things out of range. Okay, so that is the algorithm. And when you're actually doing this, you have some numbers here. We have to estimate them from the training data, but that's not problematic. Okay, so what does the circuit look like? Suppose we've been running this algorithm. The first time, I want to let S sub j denote the jth unhappy set that we found as we were running our collection. So the first unhappy set is going to be called S1. So what is the circuit that we built? It's a circuit that takes the representation of an individual I, assigns that person the value 0.5, tests, is this person in the set S1 or not? If they're in S1, their value has to be nudged. So we send them up to the nudging software, the nudging part of the circuit that does the nudging. If they're not in S1, they just pass through to the next stage. And then now S2 was the second set that was found to be unhappy. So if the current value of pi tilde, if that person is in set S2, then we put them up here and let them get nudged, and so on. So that's what the circuit looks like. And then there's this question of, well, how deep is this circuit? Like, how many iterations did we have to run for? And there's a relatively simple potential function argument that says that, remember, alpha is our unhappiness threshold, that every time you go through, you make substantial progress toward the truth P star. So we choose it's a potential function argument. We set the potential function to be the normalized L2 distance between the truth and our predictor. And every time we go through, we can prove that we reduce the potential function by at least alpha squared. So you only need about 1 over alpha squared iterations before all the sets are happy. You probably won't go for that many, because especially if your collection of sets is not very expressive, you might do an update or two and then quit, and you have what you have. You pass all your tests, but you didn't particularly get close to reality. Okay, that was the construction for multi-accuracy. For multi-calibration, it's very, very similar with one little twist. Remember that multi-accuracy said on the set, the expectation should be within alpha. Multi-calibration says that given the current predictor, P tilde, if we look at any slice, the people for any set that were assigned a particular value, you should be accurate in expectation on that slice. But it's the same argument. So here, you just, rather than looking for an unhappy set, you're looking for an unhappy slice. Your definition of a slice depends on the current state of the predictor. And then you adjust the predictor. Okay. So technical point, we have to discretize the possible slice values, because otherwise the slices will be very tiny, and we won't, by doing updates, we won't make any progress toward reality. So that also holds for the sets. And there's one other subtle issue, one issue that's actually subtle. So in multi-calibration, again, the slices at time t depend on the state of the predictor at time t, at phase t in the iteration. So this is actually a special case of adaptive data analysis. And there's no guarantee that the training set remains representative of the population for these adaptively defined slices. So if that bad situation comes about, it would ruin our estimates that we need for the algorithm. So there are two ways to handle it. One way, at least two ways. One way is to use differential privacy for accessing the data, the way we mentioned on Tuesday. And the alternative is just have a bunch more data and use fresh data every time through. Okay. So now let's recall this slide, which we saw before, where we talked about learning. And everything here you saw before. So this is telling us that multi-accuracy says the predicted world looks like the real world on average for the sets S in the collection. The multi-calibration condition is a little stronger. It says that the predicted world looks like the real world, even if we tell you what the predictions are that are made by the algorithm. So in terms of distinguishers, multi-accuracy is given by looking at experiments of this type. You're comparing, on average, OI star versus OI tilde. Multi-calibration is the pair of experimental setups that we described earlier, where the prediction itself is one of the inputs to the predictor. So again, indistinguishability of this type is captured by and is also capturing multi-accuracy. They turn out to be equivalent. We have a different distinguisher or pair of distinguishers for every set in the collection. Multi-calibration captures and is captured by the setup on the right. So you can see that this more powerful notion is captured by distinguishers that have more information. They get pi tilde. What else might distinguishers get access to? If you are auditing the bail decision protocol, what might you want access to? And if you had access, would it give you more power to tell whether this thing is actually capturing reality or failing to capture reality? Well, one thing that you might want is oracle access to the algorithm. So the algorithm's proprietary, but you're the auditor, and you say, you know, in the course of trying to carry out my auditing, I want to know, what would you have said? What would you have predicted for somebody who looks like this? What would you have predicted for somebody who looks like that? What would you do with these features? So that would be oracle access. And the next thing that you could ask for is, show me the code for the algorithm. So we're getting a hierarchy here. I'm sure that the first three levels are distinct. I don't think I know about the last two. The first two were given by the multi-accuracy and multi-calibration conditions. Once we framed these things in terms of outcome indistinguishability, it naturally suggested more tests. And we get this richer hierarchy. And there really is a difference between the second and third levels of the hierarchy. That we saw that we can construct predictors. If we're working with sets that can be recognized by circuits of size S, then we saw that we only need something like S over alpha squared of them to build our predictor. I'm sorry, 1 over alpha squared of them, each one has size S. But if we're doing this other thing where we have oracle access, then we need more. So we may need predictors whose size looks like S to the 1 over alpha. Okay. Now, so we've talked about multi-accuracy, multi-calibration. We've connected it to outcome indistinguishability. We've talked about the outcome indistinguishability hierarchy. We also gave some background in algorithmic fairness as to why we ended up looking here. This direction has turned out to be very, very, very rich mathematically. This is a small list. It's a longer list, but here are some examples. So you might, fair ranking, I'll say a little bit more about on the next slide. You might say you want to be able to predict higher moments, not just expectations in a multi-group fair way. You might want to do everything online instead of in the batch setting. You might want to create prediction intervals with coverage guarantees that hold, comparable coverage guarantees across different demographic groups. Omni-prediction, universal adaptability. I'll say more about those. Okay. So one of the things that Hannah Wallach told me a few years ago, she's a researcher at Microsoft, and she said, all this classification and scoring, no, what we really need to do is rank. We need ranking, and there wasn't a literature on ranking. So what does it mean to rank fairly when you have different demographic groups? What should the conditions be? So here's an example of something that you would want from a fair ranking system. Suppose you have two demographic groups, S and T, and on average, the people in S have higher probability of positive outcome than the people in T. Suppose you have a ranking, however, in which somehow T dominates S, meaning that in this very simplified version, we have the two sets are the same size and there's a matching, and in this matching, everybody in T is sort of matched to somebody with a lower rank in S. Okay? That's obviously unfair. So you can kind of go on and find other ways of defining other conditions for unfairness. But if you had if you built a multi-accurate predictor and then used the ranking that is given by the scores in the predictor, it would rule out that kind of unfairness that I just described. In omni-prediction, you have a collection now not of sets, but of functions. And multi-calibration is redefined appropriately for functions. You could think of sets as Boolean valued functions, and this is a richer class. And the goal is train a predictor just once, and then have the property that for all nice loss functions, nice is roughly speaking Lipschitz, for all nice loss functions L, there's a simple way of post-processing the prediction so that with the goal of minimizing this loss, and your resulting predictions will be competitive with the best minimizer in your collection C. So this is, I guess, the first place where there's a really tight connection established between multi-calibration and loss minimization. And it says if you multi-calibrate, you're going to minimize your loss as well as you could have done if you had used any of the functions in C. Universal adaptability has a little bit of a similar flavor. Your goal is to build an estimator of some sort for a source distribution without having any access to unknown future target distributions. And yet, you want, at a later time, given unlabeled samples from the target distribution, to sort of convert, make a good estimation on the new target distribution. So the traditional version of propensity reweighting requires unlabeled samples from the target distribution at training time. But if instead you create a predictor that's multi-accurate with respect to a class of propensity reweighting functions that happens to be close to the actual, contains something that's close to the actual propensity reweighting you need for your target distribution, then you can just figure out easily how to port your estimating into the target distribution when you first meet that target distribution. And you can therefore do this for multiple target distributions. You don't have to have known the target distribution at training time. Other things, it turns out there are tight connections to the leakage simulation lemma in cryptography, and in fact, multi-accuracy is essentially identical to it. There are also connections to regularity notions, strong regularity, weak regularity, that are quite interesting. There's another thing that I think is really important when you talk about fairness. if you listen to the sort of civil society discussion about machine learning, there's a lot of discussion about transparency, that that part of fairness seems to be what people call transparency. And I was pretty dismissive in the sense of I couldn't quantify transparency. I didn't know how to prove when I had transparency or disprove the claim that there was transparency. I didn't know what it was. I don't know what it is. I'm still very ignorant about it. However, think about the following. Traditional neural net training is like a lot of gradient descent. I'm going to call this micro-learning. Like we're at some little local spot and we do a little pushing locally, and it's just kind of micro. In the multi-X work, as you saw in the algorithm, we are looking for big collections of data points on which the algorithm is doing the wrong thing. We have clear statistical evidence that the algorithm is doing the wrong thing. And we fix it, one big chunk at a time. I think this is an excellent transparency story. We don't care how the sets were found. Somebody walks up and says, here's a big set on which your algorithm is doing the wrong thing. Who can argue that, yes, we want to stay with the wrong thing? No, of course, we want to update and make it better. So the transparency story is very compelling there. And I'm calling this macro learning. Yeah.
So I guess I'm slightly confused. So, I mean, earlier what you were talking about was the tension between the calibration versus some of the other fairness notions.
Yes.
So partially when you do this macro learning,
yes,
you also have the issue that you could be destroying what you satisfy
Good.
equalized odds or the accuracy of the classifier.
So, right. So when you're looking, first of all, when you're looking at scoring functions, you don't have these accuracy fairness trade-offs. Whenever you improve the scoring function, it's just plain getting better. So that's one of the reasons why I think multi-calibration took off in a way that other multi-group fairness notions didn't, like multi-false positive rate. Okay? Now, with that in mind, can you ask your question again?
So I don't know, I mean, I'm not sure if it applies or not, but I mean, certainly there are all of these results about the tension between like equalized odds and
right, so this is why, I mean, okay.
So it seems like, you know,
right.
It's true that there's an issue that's being fixed with
yes.
macro learning, but it's also not clear that there aren't other issues that are being unfixed, right?
So I don't know, actually, how to think about equalized odds or equalized false positive rates. Let's, suppose you are in a situation where you have inherent uncertainty. Then your false whatever rates are going to be very high. Okay. But your calibration could be excellent. So, yeah, so I'm not sure. Also, you're kind of mixing types, and I believe you completely when you say there's a lot of literature on it, but one is classifying and one is scoring, and they're different.
Right.
Yeah. Okay. Now, a drawback in all of this is that absolutely everything is with respect to the collection C. So, for example, with our predictors, we wanted similar behavior of the predicted world and the real world on all of the sets in our collection. Indistinguishability by tests in C. On the universal adaptability, we want to do as well on an unseen distribution as we could have done using any propensity reweighting function that was in C. And also for omniprediction, that we want to be competitive with any function in C with respect to loss minimization. And all of them have these examples. These are just going back to the ones we've talked about. So now we have to talk about C. And there's this question again, which sets, if we're thinking demographic groups, which sets? And what disturbs me, what troubles me in trying to figure out the sets, is that I don't know how to force myself to think outside the box. So for example, when we were doing this stuff, 2010, 2011, 2012, we were aware that if you had asked me, do you know that trans people exist, I would have said, of course. But did it come to mind as one of the groups that we had to be sure to list? No, it didn't. It would now. It would be inconceivable now not to include this group. But I didn't think outside the box. It wasn't in the press, also, the facts of the world change. So, now, as a disadvantaged group, maybe we should consider women who don't have access to safe abortion. Lives have changed. Things changed. So how do we, when does the set collection get chosen? It can get updated, and then you can update the function, but whose responsibility is it to make that call? Who has to say, think of this set, think of that set? And I feel that it's a little bit inappropriate to place the onus on the members of the demographic group. It takes energy to advocate for oneself and one's group. It takes time and commitment. And it also takes sort of knowledge of the fact that there is something to be advocating about. So this was a 1994 paper by Jost and Banerjee. Banerjee was one of the inventors of the implicit bias test. So justification is an idea being used to provide legitimacy or support for another idea or for some form of behavior. So you have individuals who essentially, these are like subordinated groups, who in order to reduce the cognitive dissonance between their view of themselves and the way they're being treated, is they adopt the majority group about themselves. So they accept the notion that they are less capable, even though they're not less capable, because that's the picture that's being drawn for them and has been drawn for them. So my point here is that it's not even clear that the people in the set know that there is something that they ought to be fighting about. So when I first met multiple calibration, I thought, oh my God, this is amazing. Because one of the proposals in that work was choose the collection to be all of the sets in a certain complexity class, like all of the sets recognizable from these representations by decision trees of height 6, or circuits of this size or that size. So that was great. That was like, oh my God, anything you can express succinctly, you can do this. Well, that's not entirely true. So if there are lots and lots of sets, which is kind of just this scattershot approach, we're going to say anything and that'll cover anything we actually care about. There's a weak agnostic learning problem going on here when you look for an unhappy set. So that's challenging. If the set collection doesn't have special structure or is large, what do you do? If the set collection is too large, you need too many samples. But even if it isn't that large, just some nice exponential, there's still the weak agnostic learning problem. So some people in the field respond to this by saying, we have heuristics. Neural nets are powerful. We'll use them to find unhappy sets. I'm not saying you can't. I'm just saying that there's a leap being made here. Now, there is an alternative to listing a whole bunch of sets to be sure that you cover the ones that are going to be important. And that is build a predictor that's accurate. Then automatically you'll be calibrated on all large groups. But of course, that might be difficult. Does multi-calibration give us accuracy? Not necessarily. So suppose my set collection is completely unrelated to the actual chance of success. For example, maybe each set in my collection is just a large random set. Well, in expectation, that set looks like the population as a whole. And therefore, all of the sets in expectation look like the population as a whole, and we can just assign a constant value, the population average, to everybody. I see that I'm running late, and I will stop very soon. So we don't necessarily get accuracy. Although, as I mentioned or alluded to, you can apply multi-calibration as post-processing, but then it hurts macro learning. So that actually brings up the question of, is it possible, and when is it possible, to use, say, the magic of machine learning to come up with a small collection of sets so that if we multi-calibrate with respect to them, we'll actually be pretty accurate. And I think that's an exciting direction. Last slide. What we're seeing here is kind of two philosophies, and it's important to sort of hold these up as two different philosophies. The complexity theoretic view is nature is too complex, and we can't capture it with a small set collection, we can't capture it with a bunch of efficiently computable sets, but we can find something that's indistinguishable from it. Okay. But nature is too complex. And then there's the AI philosophy, which is, why do you use neural nets in the first place? You use them because you think that they might be able to express or approximate the computation of interest, in this case, P star. And these are two different philosophies that are sort of animating some of the work that's going on, but they're not as separate as you think, because the people who say, neural nets are powerful, use them for the weak agnostic learning, they're kind of playing into this. And that's the state, as far as I can tell.
Thank you. Any questions?
Okay.
That's completely clear.
Yeah.
What's the relationship between multi-accurate and so you said
Calibrated?
does not imply multi-accurate, but I'm guessing.
No, multi-calibrated does imply multi-accurate. The other direction, no. Multi-calibrated is stronger because the distinguisher gets the p tilde values.
Oh, right, I see.
Okay? So it has more information to find mistakes.
I see. So like the second to last slide, it was the caveat of when you choose your S, you'll see totally, and it has like.
Here?
Right, yeah, choosing Q3. So does this mean like you can be multi-calibrated but not multi-accurate if you choose your C poorly?
I don't know why you're saying that, so.
So like in
I'm just saying, sorry, when I say accuracy here for question 3, I mean closeness to P star, not multi-accuracy, accurate in expectation on the sets, but just how close are we to the truth.
So forcing yourself to be calibrated can cause you to be less accurate
No,
overall.
no, that's not what I'm saying at all.
Okay.
So it's just, this is an example which says we can have a bunch of sets. I described them. They're sets chosen uniformly at random. And they have the property that if I multi-calibrate with respect to them, I'm not getting very close to P star, because there's a sort of trivial multi-calibration algorithm. So if multi-calibration is going to actually help you along your way to getting closer to P star, it has to be because something in the set collection is correlated with expresses can separate those instances that are more likely to have a positive outcome from less likely. Then your multi-calibration will cause those to get different scores, those two different kinds of people to get different scores.
So wait, but then I'm confused. So let's say that we have one set.
Yes.
It's got like 2/3 label as 1,
Yeah.
and then 1/3 is label as 0.
Yeah.
So if I started off with the baseline predictor that predicted 1 for everybody, then it wouldn't be calibrated, and I would sort of push down on the probabilities, right? And so I would have to push down until I reached 2/3. But then that 2/3, if I took it as a prediction accuracy, that would actually be worse in terms of accuracy than the initial predictor that I started off with, no?
It's accurate in expectation. Among those for whom you predicted 2/3,
But
okay.
So that would be accurate in terms of averages across the entire thing, but not in terms of the individual labels on people, right?
So I'm having cognitive dissonance. I can't do arithmetic on my feet. However, there is a theorem in the multi-calibration paper that says that the updates that you do for calibration purposes do not hurt accuracy overall. So, what you're saying shouldn't happen. And I don't know,
I think the issue might be the definition of accuracy.
Yeah.
what's
So-
your definition of accuracy?
So how, for each individual person, do you get their label correct?
So I want to look at this formal definition, the L2 squared distance. And by the way, what do you mean you get their, they don't have a label. Do they have a label?
Yeah,
So 2/3 of them have a true P star, which is
1.
1.
Yeah.
And,
The other 1/3 have P star, which is 0.
okay. And they all start with a P tilde of a half.
No, just let's say you start off with 1, right,
Okay.
for everything. So you have a classifier that has accuracy 2/3 because it's predicting everyone is going to have the category 1. And then if you pull it down to try and calibrate it, you're going to have the effect of actually hurting the overall individual by individual accuracy.
But you won't hurt the L2 accuracy.
Right. I mean, it's a question of whether you average over the group or you look at the actual accuracy on the individual people. So I think the potential function you have there is like, averaged over the group, which is true because if you're off, then you improve it, right? But, sort of what I was getting at with the tension with the fairness issue is that, like, if you look at an individual basis or the individual accuracy, there is the issue, like, that by calibrating, you can actually hurt the individual accuracy. So it's kind of, one of the tricky things, I think, is, like, figuring out what the prescription is
Right.
in light of the fact that, like, you can't achieve multiple criteria at the same time. It's maybe, at least I don't really know what to do in such scenarios.
Right. We don't know what to do in those scenarios. And the one thing we don't want to do is restrict our choices to saying it has to be one of the three.
Sure, yeah.
Right. Yeah. Right. Okay.
Yeah.
Good.
Okay, thank you. Thank you for this set of 3 lectures.
Thank you.